Okay, you said 44Z? Okay, 44. Looks like we had some kind of curved ramp in this one. My book. Alright, this one said, up and down a hill. A 28-kilogram rock approaches the foot of a hill with a speed of 15 meters per second. This hill slopes upward at a constant angle of 40 degrees above the horizontal. The coefficients of static and kinetic friction between the hill and the rock are 0.75 and 0.2 respectively. Use energy conservation to find the maximum height above the foot of the hill reached by the rock. So that's the first thing we're asked. So we were given coefficients of friction, so obviously we can't ignore friction, right? So, and it specifically says use energy conservation methods to do this. So at the foot of the hill where we started, I just drew points A and point B right here. The hill hasn't inclined yet as I approach it, so the left side of my equation will have kinetic only, right? And when we do have work done by any other forces, we put them on the left side typically. I include them. So we know work other is being done by friction and specifically kinetic friction. Looking at the number again, yeah. Okay, so I'll blow this up a little bit because it's kind of a little bit small in there. But position B, once we reach this max height, and the way it was asked was to find the maximum height above the foot of the hill reached by the rock. And that is exactly what would be the height considered in our potential energy that we get to. Because when we first introduced our potential energy function, I just called this H the height at point B. When we break down potential energy to mgy generically, y was always the vertical distance down, even if we were on an incline, right? Or a hill like this thing. It's always represented in there, so that's what we need to solve for. And from the next step, I just broke down those equations. So the kinetic energy is 1m times the v we were moving at, which was given 15. So we'll have that to plug in later. Mass was given in mg, and there's a height we're looking for. So the work other done by friction. Friction is a non-conservative force, and it takes energy out of the system, right? So if it wasn't there, this thing would have went higher. So this was also something noted somewhere in the past when we went over this. When we have to plug it in, either as an expression or a given value, the work other, if it's work done by a non-conservative force, I got to make it negative. So you can see it does say add in the generic formula, but that's because it's the generic formula. That work other could have been work done by something pushing it, right? And that would have stayed positive when I plug in anything, value or expression. So we have to remember that if it's friction, that's a non-conservative force doing work, taking energy out of the system. So that's why I have to make sure I include a minus there on the expression for friction. But that expression for friction, that's what made this one maybe a little tricky. In general, we know the force of friction is mu, in this case kinetic for this part, times the normal force, right? Let me blow this up a little bit more so we can see it. The normal force, though, from the past, we should know on a hill or an incline is not equal to the weight. It's equal to which component of the weight? Perpendicular, or the y component, you could call it as well. We called it either in the past, but we got to make sure we remember that. And that perpendicular component has its own formula that was mg times the perpendicular was cosine theta, okay? and theta is 40 degrees, the slope, consistent slope of this hill, as it said. But also, that term right there takes care of the force of friction, but the force of friction acts over the surface it's sliding along, right? Or moving along, in this case. And we don't know that. It's not this because it's not moving along a surface that is vertical along this, right? It's moving along from like here to here along an incline, right? So we treat this basically like a triangle, okay? So we end up getting the displacement I'm going to call S in terms of this height when we draw a triangle, right? So that was probably the trickiest part of this problem. So I get an expression for displacement S along the incline that the friction is acting just using SOHCAHTOA, and I find out an expression for S in terms of what we're looking for, H sub B in that case, is H sub B over sine of 40. So does that make sense why I plug that in there to everybody? Okay. Once I plug that in there, and the fact which I already mentioned that FG perpendicular is mg cosine 40, we could start solving this. Okay, we'll notice that m cancels out. It was given, but it can cancel out now since this is in every term. And looking through what we have left, everything's a constant or a given other than HB, but it's in two different terms, right? So just do your algebra. Get every term with that H sub B to one side, factor it out, and move the piece out by division. And there are some steps skipped there, but that's because they're all algebra ones you should be able to handle. All right, so we get an ugly expression, but we have an expression where we isolated H sub B where we could plug in all givens and constants. If we do that carefully, we should get out 9.3 meters as the vertical height at which that reaches under these conditions. Does that make sense? All right, in part B, it says, will the rock remain at rest at its highest point, or will it slide back down the hill? Okay, so we know where its highest point is. And for a moment, if it does slide back down, we would have to know that it still would have to stop for a moment to change directions, right? So it would have to come to a complete stop for at least a moment. It may stay there. We don't know yet. We got to solve. But even if it did come back down, it still has to stop there for a moment, okay? And when it stops for a moment, it's at static friction, permanently or for a moment, I should say, right? So I drew a free body diagram at the stop position up here. And what we need to consider is what is trying to pull it down the hill? What force? Right? What component of it? Remember, we're still on an incline, so there's two components. Perpendicular and the parallel, right? The parallel component of gravity is what's trying to pull me back down, right? And to answer this question, books? Just throw them. Actually, yeah, that's fine right there. That's probably what they are, SAT books.
Merry Christmas.
Thank you. All right, anyways, guys. So basically, at this point of this problem, it's really an old problem. No energy methods here. We got to decide what the static friction is that wants it to stay, right? And compare that to the parallel component of the weight, which wants to pull it down. If parallel is greater than static, gravity is going to win, at least that component of it, and it's going to come back down, right? If not, then it's going to static friction is greater, then it's going to stay. So the first thing I found out here was that FG parallel. That's the only force wanting to pull it down the incline. It's a little bit over 176 newtons. All right. So next I would have to find static friction. The max, if you recall, going a little bit back, Making this an equality means finding its max. The original generic equation was an inequality that FF static was less than or equal to mu(s) times normal force. But as an equality, that making it the equality, not the inequality, that makes it at its max. That was stuff from the past. All right. So plugging that in, the given mu static from above, and the fact that, again, friction is mu times the normal force, but the normal force is perpendicular, is equal to the perpendicular component of the gravity, which is mg cosine theta. Multiplying that all up shows me that the max static friction is only 157.7. So the static friction, when it stops there for a moment, is not enough to keep it from going down the hill, because they're playing tug of war on each other right there, right? This one's going to win. It's going to come and start moving back down the hill. That make sense? This one overall was a little tricky just to realize what you had to do to get to these things. Some old stuff there that wasn't just, didn't have anything to do with energy in part B. All right, we good so far? All right, part C. Let's see what we got in this one. If the rock does slide back down, which we now know it does, find its speed when it returns to the bottom of the hill. All right, so now we're just reversing the energy process. Now we go from, we still have friction, right? And now it's in motion and moving. We're going to use kinetic. But now we go from potential, right, to kinetic at the bottom with friction acting, still a minus right there because it's taking energy from the system. Now, this would be a really easy question if there were no friction or no outside forces. What would just the answer be with no work if there were no friction when it came back down? 15, right? That's what theoretically it would be. But since there's friction both on the way up and on the way back down, it's going to be less than that. All right, so considering that and putting in the similar expression for friction, we could use the same one we found above, right? Because it's going to be the same s distance along the incline, so we could just transfer that ugly expression from above and put it there. And again, mass cancels. This time V's what we're solving for. And isolating V when it gets back to position A is going to be 11.8 meters per second, which makes sense. If you got an answer out higher than 15, you know you're wrong, because there's no way that could happen unless there was an external force that shoved you down the incline or something like that. So it makes sense that this is a reasonable answer if you understand just the concepts of the problem, that it's got to be under 15. Does that make sense? Okay, no problem. We just went over one problem that there was a question on. It was 44. If you happen to have a question on that one, the video will be posted, all right? All right, other questions? Brandon? 76. Okay, so this one relates to that stuff with potential energy functions I missed. And knowing the fact that if we are given a potential energy function and want the force at any given moment acting on the object undergoing that potential energy function, we take the negative derivative. That led us into the fact of why peaks and valleys on a graph are considered equilibrium positions. Because if we take the derivatives there, they're flat lines, right? Zero, and we call, in the past we've called equilibrium situations when force was equal to zero, hence acceleration equal to zero through Newton's second law. All right, so anyways, a particle moves along the x-axis while acted upon by a single conservative force parallel to the x-axis. The force corresponds to the potential energy function graphed. You can see it below, and I redrew a rough version of it right here. The particle is released from point A. What is the direction of the force on the particle when it's at point A? So I have a little star based on this one. Remember, the force isn't just the derivative, it's the negative derivative, right? So we could see from the graph, we got to understand like we've always in the past, derivatives graphically. All right. At point A, the line drawn tangent to point A would have what kind of slope? A line drawn tangent to point A, which is graphically represented by the derivative, would have what kind of slope? Point A is right here, right? A tangent line would go like that. It would have a negative slope, right? But we take the negative derivative. So if the derivative is a negative slope, it actually flips it for the force, right? So for answer A, like just have it summed up right there. The tangent line would be negative, therefore the force is positive due to that fact right there. All right. Part B. What part B said? Same question, but just at point B. At point B, the tangent line would be an upward positive slope. So the negative derivative would be flipping that, and it would be negative. The force would be. And one reason we related it well to springs, just to remember the concept so it's not just a fact. The reason it's the negative derivative and not the derivative is because forces, conservative forces, like to pull things to a lesser potential. So like when I stretch a spring, where does a spring want to pull back to? Back that way, right? And that would be, if I call this the positive direction, that would be the negative direction. And it forces it back to a lower potential when it does that. That's the kind of idea of, conceptual idea why that formula is the negative derivative and not the just plain old derivative. The plain old derivative would give you the correct magnitude of the force, it just wouldn't have the right direction. Okay? Letter C. What did that one say? At what value of x is the kinetic energy of the particle A maximum? So we would have to look at this thing and find the least potential, or at its min. And from that graph, it looks approximately, each one of the markings on the x-axis, you would have to look at the one on the book now because I didn't draw in the numbers on this one. I just drew a rough one. The lowest possible position is this one right here, right? And that occurs at an x value of approximately 0.75. It's not on a perfect spot, so I think it's a fair estimate. It looks like it's right between 0.5 and 1, so 0.75. And that just follows along the idea of energy conservation. Applying it to really anything, but let's just apply that idea to not that. I thought that was my pendulum. A pendulum real quick. All right, so where's kinetic energy the max? When potential is at its lowest, right? Where's potential is lowest for like a swinging object, right, as it passes through here, right? So if energy is being conserved, then if there's no potential, it all has to be kinetic right there, and that's where you'd be going the fastest as well, since it's the energy of motion. All right, letter D. What is the force on the particle when it is at point C? That's a peak. Tangent line would be flat, so the force would be 0. Letter E. What is the largest value of x reached by the particle during this motion? I mean, it's the largest value for x, the position, so I don't know, kind of odd question to ask. It's very simple. You just look where the graph ends at the x position, and that's approximately 2.25. All right, it ends around there. Just reading the graph on that one. That's all. F. What value or values of x correspond to points of stable equilibrium? So we said peaks and valleys are equilibrium, but which one's a stable equilibrium? On the bottom, the valley, right? And the best way to just remember that is we said, imagine if this was actually like physically a track, like a roller coaster track is the easiest way think of this. If you displace something to the left or right of stable equilibrium, it wants to go back to the equilibrium position, right? If you displace it on a point of unstable equilibrium, right or left, it would fall off of it, right? And not naturally want to come back to it, kind of thing. So therefore, yes, that position right there, which was about the 0.75 position, the dips. Oh, and there was two of them, actually. Sorry, I forgot about this one. There was two. This one here would be at the approximate 1.8 meter mark. As long as you're close to that, since you have to kind of estimate a little bit, that's fine. And the only unstable for part G, the only unstable equilibrium position, again, is that the only peak we have is right here, and that would be approximately 1.4, or very close to that, whatever you estimated. You good on that one? Other questions? Biggie. 42. Oh, this is a good problem. A few years back, this almost identical problem came up on the AP test. Very similar to this. Brings in some, remember I mentioned to you guys, like on the open-ended AP ones, they love putting problems on there that have multiple concepts involved. Not just an energy problem, but like this one has energy involved and circular motion. Because since there's only 3 open-ended ones, they try to get a lot of stuff in by putting things in with multiple stuff from different chapters or units that we covered. All right, so 42, riding the loop-de-loop. A car in an amusement park ride rolls without friction, so we could ignore that, around a track. The car starts from rest at point A at a height, vertical height h is defined right there for us at point A. That height h also, the picture in the book's much better. That height h is also supposed to be where the bottom of the loop is. All right, it looks better in here that you could tell that in the actual picture. Treat the car as a particle. Part A, what is the minimum value of h in terms of r? So we don't have numbers to plug in. So again, this is another great problem at this point for that reason. Many of the open-ended ones don't give you numbers to plug in on the AP test because that way they force you to do the ugly algebra so you can't cheat and plug in the numbers early and cut down on a lot of the crazy math that goes on here. I'm not saying that happens all the time, but that's another reason why this is a good problem to force you to do that. So we want h in terms of r, so the car moves around the loop without falling off at the top at point B. The minimum, or essentially, back when we did circular motion, a big important concept here once we get to that circular portion of this problem where we're in that loop. When we had vertical loops going on, there was always some minimum value, sometimes we were asked to find, of the speed necessary to get it through, otherwise it would fall, right? Now, of course, on an amusement park ride, they're designed to go plenty faster than the minimum speed in most cases. But even if something bad happened, you're not going to fall down. There's wheels that walk around the backside of the track just in case something weird happened that slowed you down for some reason that you wouldn't fall straight down. But if that safety feature wasn't there, if you went too slow, you definitely could just fall down like that thing, right? But the main thing is, we got to remember, a lot of things in this problem, as far as just getting through the loop, at that position, the top position is what matters the most. And for a simple minimum speed problem that only asks that, think free body diagram for circular motion at the top right here. All right, let's actually use this thing because it's more like the roller coaster loop, right? So what is the force making this go in a circle at any moment once it's in the loop? What's that? No, what is the force making? Well, we only use momentum we didn't even learn about yet. So, yeah. Well, you're right, it is centripetal. But if you recall, centripetal is like a general category of forces, right? If you're going in a circle, there's got to be a centripetal force on you. But many times, most of the time, we have to break it down and identify the specific force that is centripetal. All right? Centripetal is just like a category of a force, any forces that are making you go in a circle. So what is physically making this roller coaster cart go in a circle? What force specifically? Now, if it were this thing, it would be what? Tension, okay? And since it's a vertical circle, it does interact with gravity. We'll bring that in. But what's the specific? If we took this away, gravity's still going to be there. And gravity's not going to make you still go through a loop, right? If we took this force away, this thing would fly off. Remember, tangent to the path? What is physically making the roller coaster go in a circle? If the track wasn't there, would it go in a circle? Normal force, right? The track pushing back on it. Okay? So, back when we did problems like this, the free body diagram at that position would include normal force pointing where? Down, because the track's on top of us, right? Normal force that way, and weight always has to point down, right? And we could say those two added together, since they are pointing in the same direction, we yet total them, through Newton's second law equals m times the centripetal acceleration. I remember doing that? And to find the minimum, we would actually set the centripetal force, in this case normal, which we identified, equal to what? At that moment, we would set it equal to what? Anyone recall? 0. Because to just make it through, you actually, remember this is very quick, very momentarily, all right? You would actually, for a moment, if you do just make it through, you'd hang freely for that moment at the very top of the thing. That's why we set that equal to 0 to solve for the v necessary to just get us through. You wouldn't fall because you just passed through that at that moment, and then you're into the next part of the curvature that does push back on you. All right, so that's something that needs to be remembered to, or considered, both mathematically and conceptually for doing this stuff. All right, but it's also intertwined into the energy problem. All right, so what we know, conservation of energy wise, point A is the dropping point, right? Point B is what's in the point we have to go to, because that's the position that matters if we're just going to make it, right? That vertical top position, we need to find the minimum velocity based on the ideas of that position. So that's going to be point B, which they already identified point B for me there. And one other thing it gives us in the picture is the radius of the loop. It's a consistent radius. It's a better perfect circle in your book. But one thing is, if the radius is r, and that's a uniform circle, then we could actually say that point B is 2 times r from the bottom of the track, right? Remember, it told us specifically, the picture in the book's better, that so that's like our reference level right here, from here to here, how high we are off. H is how high we are off to start. We're clearly lower at point B, but we could get an expression in terms of something given, which is r. Because if we took that, now if this were a more of like a elliptical loop, we couldn't do that, right? But since it's a perfect circle loop, you could see in the diagram, we could say it's 2r. All right, so anyways, we start all with what kind of energy at point A, since we were dropped from rest? Potential, right? Gravitational potential. At point B, we're using, down here as the reference level, we would still have some potential, right? But we're moving through point B, so we also have some kinetic, right? So we put all those expressions. So we start with mg. H is the vertical height they defined for us over here. And we mg 2 times the radius over here. That's what we already said, right? For that potential energy. And then 1/2 times m times the velocity at point B right here. Masses can all cancel. Get rid of those. All right? So now is where we get into what I just discussed and reminded you of just making it through a vertical circle. So over here, I drew the free body diagram at the position, okay, at the B position, which I already said would be normal force and weight, right? Another thing direction-wise we did back then. You don't have to do it this way, but it was the easiest thing to do to make the math and signs in the math as simple as possible. You might not remember this. Maybe you do. Hopefully you do. One thing we did with vertical circles was always made the positive direction the direction towards the center. So that means actually at different positions, the positive direction could change. If I'm at the bottom, up is positive because towards the center is positive. If I'm at the top, down is positive because towards the center is positive. And the reason we do that, if you don't do it that way, then you have to, if you're using Newton's second law, equaling it the sum of the forces to m times the centripetal acceleration, you would have to account for the changing the direction on the a in that formula, which most people forget to do if they do it that way. So basically, that goes back to why I don't have any negatives in here. All right. So we would add those two forces together, and they would equal mass times, I have r there. Remember, centripetal and radial meant the same thing, right? So normal plus weight equals m times the radial acceleration. But I didn't include the normal for reasons I just said, but it's noted here. If I want to just make it through, it would be the moment the normal is 0 on me, right? Leaving me with just the force of gravity equals m times that acceleration. All right, force of gravity is mg, right? mg, that m and this m over here from the right side of Newton's second law cancels. Centripetal or radial acceleration is the velocity you're moving at squared divided by r, right? So there's another old thing with circular motion we got to remember. So I could get an expression for VB solved through this formula of Newton's second law setting up correctly for just making it through the top of that circle, square root of g times r. I'm going to sub that in for that v, and it gets squared, so that takes away the square root, doesn't it? So that's where I get my gr there. And to answer this in terms of what it said, we only wanted the minimum value h in terms of r. And if you didn't remember all this, you'd still have the v's hanging around and all that, and that wouldn't satisfy the problem, right? We want it only in terms of r and any possible constants that exist. That's always kind of a given, okay? So once I do that, I could combine some like terms here, gr and gr, right? 2gr, 1/2 gr. And the g's could cancel out at that point because it's in every term, right? And that condenses down 2 plus 1/2 is 5/2. H equals 5/2 r. So in order to figure out, as long as friction is negligible, we could generalize this to this thing. As long as friction is negligible or not present at all, we could figure out the height needed to make it through a circular loop through this formula. 5/2 times whatever the radius of this hoop is. That would translate to the minimum velocity that goes from potential into kinetic at the top position needed. That makes sense? Like the whole reasoning behind it to get through there, which didn't happen. I hit my phone. Anyways, to get through that, which that would have been too low. All right, so very good problem. I know there's a couple parts left, though, that intertwine energy to a whole other concept we had. Any questions on anything in that part? Definitely tricky. There's a lot to it. Okay, part B. If h equaled 3.5 r and r equals 14 meters, compute the speed, radial acceleration, and tangential acceleration of the passengers when the car is at point C. And I say point C is right here along this side. Okay? And this one's should be a little bit easier here. So we're going from point A, which is still the same original point we talked about before, which has all potential right here, right? mg times that height h. And we are going to have both potential and kinetic at this position right here, right? Now, at this position, again, looking in the book, it's more clear. This position is right across from the middle, right? So its vertical height would just be what down to the bottom? What's that? R, exactly. Everybody see that? But if we're right along the side here, or here for that matter, all right, the vertical height is just the radius itself. So that's why I have MGR right here. All right. Again, it's a generically MGY, but the Y distance straight down is equal to whatever the radius is. And we're going to have some kinetic energy there because we're passing through it. So the kinetic energy is 1/2 m times the velocity at position C squared. So the first thing it asked us, based on given radius, masses cancel out. They didn't give us mass, so it better cancel out. First, compute the speed there, so I solve for V. Isolating V gives me this expression I could plug into, and throwing in the numbers, I get 26.2 meters per second, or something very close to that. Okay on that? All right, so for the radial acceleration, that at that moment is V squared over R, right? So that's easy as long as we got the first part right. That's dependent on that. We plug in that 26.2 squared, divide it by the radius, which was given as, is that right there? 20? Oh, you know what? Something just popped into my head. I think last year, remember, was the first year we used the new books. I told you guys. And I think the old book, the R was 20. And I was thinking the old problem and still put in 20 there. Let me double check that. Let me see if I just made a dumb mental error. That could be right still. Hold on. The work's right there. The idea of the work's right. I just might have messed up because the old version of the book and the new version just often changed some of the numbers, but still were the same problems. Yeah, that's one I never fixed. So this should be actually, I think I even made a note of it last year and forgot to go back and fix it. Okay, yeah, so that 26.2 is still good. Because you could see up here I used 14 for R, right? For whatever reason in this step I plugged in 20 and that's what the old book used to have. Alright, so that should be 14 right there. And squaring that 26.2 and dividing by 14, the answer should be around 49 meters per second squared. Let's make a note of that. I'm going to write that down to fix. Maybe I'll remember to this year. I tell you what, if you need a break, bell rang. All right, last thing, what we found here, which we fixed. So that is now, what did we say? 40, right? Or 40, 49 meters per second squared, but when we fix that radius. Okay, that's the centripetal or radial due to changing direction, right? Now, this, something like a roller coaster going around a circle, is not in uniform circular motion. If you recall, uniform circular motion is going through the circle at a constant what? Almost. You can't say velocity because direction always changes though. Constant speed, right? But on a roller coaster, because there's nothing like giving you an extra push through, because of the reasons of energy, which we've been talking about, you're at its fastest right here, right? But as you go around and reach the top from here to here, you're slowing down, aren't you? And then from here to here, you're speeding up again, right? So this is not uniform acceleration. This is not constant speed, so it's not uniform circular motion. So at this position C, where C looks like we're right here on the way back down. So we're speeding up again, tangentially accelerating. So which is separate from this acceleration that we found. Okay? So once we find both of those, this problem is going to ask me to show these two acceleration components in a diagram. It says approximately to scale, but I don't care that as long as they're pointing in the right directions, okay? But we need to figure out how to find at this position the regular old acceleration that's due to speeding up or slowing down. We found centripetal, they're two separate ideas basically, right? And sometimes we refer to that as tangential acceleration because it's speeding up or slowing down at any moment tangent to the curve. All right, so I'm going to take and make a free body diagram at position C. Again, right there. So we're on our way down, but forces on me at position C would just be gravity down, and there's still the centripetal normal force making me go through the curve, right? Which always points towards where? The middle, the center. That's why it points that way. However, I'm looking for my tangential acceleration, which would lie on the y-axis, right? So remember in the past when we used basic Newton's second law, we only use it on one axis at a time, right? Since this force is completely on the other axis, is this at this position, maybe this wouldn't be true at other positions, but at this particular position, does the normal force from the track have any effect on my tangential acceleration? No. My tangential acceleration, this is showing me and understanding it through this free body diagram, is only due to gravity, right? Which then proves a simple little fact at that position only. But if I set it up, there is only one force on the y-axis, so I'm summing up all the forces on the y-axis, and the acceleration, the tangential acceleration, is tangent to the y-axis at that moment, so that's why we can plug that in there. And obviously weight, or force due to gravity, equals mg. Masses cancel, proving to me that this tangential acceleration is only due to the acceleration due to gravity. Therefore, it's 9.8 meters per second squared. Make sense? Now, it doesn't ask. It would be a lot trickier, though, if it asked for the tangential acceleration right here. It wouldn't be a lot trickier. It would just be trickier. The reason why is because now, like somewhere here, or anywhere that isn't like right across, it's trickier because the normal force might be pointing something like this, right? And now the normal force would actually have a component effect, right? Not the whole normal force. So what we would have to do if it were not at that nice convenient position C, we would have to break normal force up into its components. And the y component would be part of my sum of all forces here. It could still be found. It's just more work to it if it were changed. All right, so after I have that and prove that it's 9.8, well, that's the most important thing. It does say show the components in a diagram. I didn't do that. All I care about is you could find these. If you showed it in a diagram, you would just draw them. You would draw this one. If you draw it as a vector arrow, it's pointing towards the middle because it's centripetal, right? If you drew the other one, since we're on the way down, it would look like that. All right? But most importantly is being able to find them, which we did right there. Again, we fixed that one for the correct radius. So, yeah, that was a pretty big, ugly problem. All right, other questions? Keep going if you have them.
Actually, 39.
39? All right. A block with mass 0.5 kilograms is forced against a horizontal spring of negligible mass, compressing the spring a distance of 0.2 meters. When released, the block moves on a horizontal tabletop for 1 meter before coming to rest. The force constant K of the spring is 100 newtons per meter. What is the coefficient of the kinetic friction mu K between the block and the tabletop? All right, so we do have work other right here in the form of friction again, right? often many problems, kind of variations of this problem are often given on the AP tests I've seen in the past. Pushing something against the spring, letting it go, the spring pushes. One variation I could think of, I think you have one like this in the review we do eventually for the AP test. It has this, but it brings in circular motion because it brings in like a heel that's a bump like that. So it would have like similar features to what we did on the last problem. But so there's a lot of variations they like to give on problems like this. This is a good one as well. So if we push it the whole way back and then release it from rest, we only have, there's no gravitational potential because we're not like doing anything vertically, right? So we shove this spring and compress it back to a position right here. If it's released for rest, we'll call that position 1. There's no kinetic. We only have potential elastic, right? And there is going to be friction, so we'll include it. And remember that we have to make the expression we include in the next step negative. We talked about that in another problem before. And then if later on it completely releases it, position 2 is where it comes to rest. So let me just make sure I did it the way I think I did it here. Yeah, all that, I just don't have it marked right here, but down here in this step I do. So if the spring completely releases it, there's no more elastic at position 2, right? It's away from the spring. It's not acting on it anymore. Also, it comes to rest, so K2 is what? 0. So in the next step, everything's 0. I have this whole expression on the left equal to 0, right? So at that point, I'll plug in the expression for work due to friction, the force of friction times the displacement. The displacement was given. It goes 1 meter from here to here till it comes to rest, right? So force of friction is mu k times the normal force. Normal force, since it's just a plain old flat surface with nothing crazy going on, normal force just equals the object's what on a flat surface with no like angled pushes or pulls? The weight, right? So that's what I'll plug in eventually down here. Normal force equals mg. So plugging all those expressions in and solving for the only unknown now is mu k. Isolating it, popping in all those numbers, we get out 0.41 must be the coefficient of kinetic friction. You're all right on that one? Okay, no problem. Anything else? All right, so did we say, is Tuesday a red day? Yeah. Okay, so you guys could take the test in here, but still get to take it home with you since Spencer's at home as well, and turn it in by the end of the day, 11:59. So you'll have both tours to work on it. If you get done, fine, turn it in class. Yeah, I'm still, since some are home, some are here, I still am going to, you could just do work on your notebook paper and take pictures of it, even if you're in class to do it. Just for, it's easier for me to collect everything the same way. What's that? Yeah, squid's fine too. Squid or picture is okay. Okay. Tomorrow we're going to, I'm going to give you for the remote day one of those ed puzzles to the new topic. It's not a big one, like 20 minutes video. Actually, some of you, it's a really good video on the next topic. Some of you might remember that had advanced last year. I usually show the same one in both classes because it's really good on the next topic. You remember the car crash video from last year? It's that same one, but it's on an ed puzzle to ask pauses and ask questions along the way. But that's the next topic is momentum and inclines. So just to give you a little bit of background today before you watch the car crash video, I'm just going to, for a moment, speak of a couple things, ideas, not get any in full detail. And we're going to watch two short videos here, like a 5-minute and a 10-minute one. And throughout the next week to 2 weeks, we'll be mostly spending it on these ideas called momentum and impulse. So momentum, anybody know what it is or remember from last year? Well, you're really close. as a matter of fact, one way Newton himself described it was inertia in motion. So if you recall, when we first learned the term inertia, things that had more inertia than other things simply had more what than other things? Inertia is directly tied to what physical feature characteristic? Yeah. Mass, exactly, right? So, but when that mass is in motion, we put, hence therefore, inertia in motion. And it still goes back to the main concept, basic concepts of Newton's first law. We already went over way back when, but we're just going to define it in terms of what's called momentum now. When we take some given mass that has a certain amount of inertia, if I throw it very lightly, Z, catch. Close. All right, but you weren't that scared because I didn't throw it very hard, right? All right, but if I take the same mass, same inertia, right, but throw it a little harder, not that hard, you got to be a little bit more ready, right? Because that throwing it harder, it wants to stay in motion more than the one I threw at Z that I just lobbed at Z, right? So that part of it, that aspect of it, is really describing what we simply call momentum. And momentum itself is very, very simple formula. Anybody from last year happen to remember it? It's just a product of two things. Really, the two things we just talked about here. Velocity and mass. P, and actually the symbol for momentum is lowercase p. I really don't know why. I never heard why. It's just like, probably because it was just assigned to it because all the other M's were used for mass, so we wouldn't want to use it for momentum. So for whatever reason, lowercase p got assigned to represent momentum. So P equals mv. Now, since it's such a simple idea, we're not often just asked to find the momentum of something traveling. So that's very elementary, right? If I give you the mass and I give you the velocity, you multiply them and boom, there you got it. And it has ugly units that were never renamed. But remember, we want masses in kilograms, right? And we typically have velocities or speeds in what? What's our typical unit? We always want that in meters per second, right? So when you multiply those two units together algebraically, you get kilogram meters per second squared. I'm sorry. Kilogram meters per second. I said that wrong. Because a kilogram meter per second squared is a Newton, was renamed a Newton. This never got renamed. It's just a kilogram meter per second. So that's our typical unit on momentum. There is another valid unit when we get into the math with impulse, which I'm not going to get into right now. But what we often care about is not just finding the current momentum of something. That doesn't do a whole lot for me. Just finding only the momentum and just giving that. But what matters really to us the most is when momentum changes. So when I throw this ball at a wall, when I released it from my hand, it had an X amount of certain momentum. Okay? When I released it, it would travel, since there's not going very fast, air resistance is pretty insignificant, right? So if I release this mass, whatever it is, from my hand, we could assume that it went at a pretty constant horizontal velocity till it hit that wall, right? So the momentum was pretty constant until it hits the wall, right? Then we could say the momentum definitely changed, didn't it? It's still the same mass. It didn't come apart. Sometimes momentum can change when it strikes something, though, because sometimes the thing can fall apart, right? So sometimes momentum could change due to gaining or decreasing mass. But I don't want to say we won't have a problem with that, but those are more rare cases. Most of the time when things come into contact with something else, they stay together most of the time. For the situation we're going to look at least. But what will change the momentum will really be the fact that the collision changed the what? The velocity. Okay? And when momentum changes during that process, and in many cases it's very quick, the process that changes this object's momentum is when it's in contact with that wall, right? That is a fraction of a second, isn't it? Sometimes the times are going to be extremely low during momentum changes because it's brief contact, like hitting a baseball. That is like milliseconds, basically, that it's in contact that causes it. But of course, hitting the wall is what changed the momentum of this thing, right? And then it came back to me, whatever new momentum from that change in velocity that occurred. But the wall has to apply a what to change its momentum? A normal force, but in general a force, right? Something has to apply a force to change this object's momentum. Again, that doesn't sound too much different from when we described Newton's first law a long time ago. Acceleration is also changing if we change its velocity, right? But we're just looking at specifically momentum change now. And a force is needed to cause a momentum change. Something's momentum will not just magically change, okay? And that force, whatever it was, had to be applied over a certain amount of time. And that brings in the other main aspect we'll dive deeper into next week of an object's delta P, change in momentum, is equal to what's called the impulse, what actually changes the momentum, the product of force times time. So if you take the force the wall applied on this ball when it hit it, multiply it by the time in contact, which is very tiny for this idea, that impulse, we call it, equals mathematically the exact same amount as the change in momentum. mv final minus mv initial. All right, that's going to eventually be called the impulse momentum theorem. That those two things equal each other. We're going to give many examples of this as we go. There's tons of examples with sports in this because a lot of sports involve collisions, right? There's in car crashes. That's why you're going to see that video tomorrow, because car crashes, something that unfortunately happened a lot, right? And this is the main physics behind it. But we'll give many other examples next week when we get into problems with this. So that's my little intro to this stuff. There's a lot more to discuss with it. But I'm going to stop my recording now, and for the last few minutes, watch these like 5-10 minute videos that tell you a little bit more about it.